How might you put a telescope in a circle that is more noteworthy than the rocket that is going to ship off? Is it basically even possible, imagining that it is critical? All that exists in space, or if nothing else in our planetary gathering, is now there to the degree that we know. Everything in space is exceptionally old, so the chance of something else length appearing there seems to be extremely unimaginable. The opposite is substantial. The James Webb Space Telescope, by taking unfathomably careful photographs of the universe, has caused quite a sensation in general. The brilliance of science is that it welcomes new information rather than excusing it. Despite the warm assembling to new information, some of what the telescope is seeing is at this point frustrating and confounding. What have analysts taken note of from the James Webb Space Telescope that has them confounded? What secrets about the first light of humankind, to the extent that we may be concerned, has the telescope opened up until this point? We ought to find out. As of late, NASA, the European Space Agency, and the Canadian Space Agency teamed up to give cosmologists all over the planet an extraordinary gift and valuable opportunity to brief investigate the past at the creation of the universe and the edge of time itself. The James Webb Telescope, hailed as the central observatory of the following 10 years, remains as one of the greatest intellectual achievements in recent memory. It opened this strong window into creation, not as a philosophical theory, enchanted time machine, or innovative portrayal, but as a significant instrument. On December 25, 2021, this tremendous infrared telescope, all the more generally known as Webb, was launched. It was determined to get photos of the dark and uncover the secrets of our mysterious universe. The state-of-the-art infrared equipment outfitted on Webb works on the unique perspective of the universe that Hubble has given humankind, revealing the hidden universe to our eyes. From its vantage point in low Earth orbit, Hubble has gotten various, as of not long ago, never-seen pictures of far-off regions and remarkable seasons of our universe, examining the history and progression of astronomical systems, stars, and clouds. It has depicted the characteristics of black holes, exoplanets, and the accelerated expansion of our universe. This groundbreaking work earned the Nobel Prize in Physics in 2011. Webb represents the next step in our total understanding of the universe's insider realities and searching for life beyond Earth. Hubble's pictures have described modern cosmology, opening our eyes to what lies beyond and igniting our existential curiosity. As NASA puts it, if we want to see farther and more significantly, Webb can peer back to the beginning of time, while Hubble can go as far as 500 million years after the Big Bang. How could this be possible? The most recent space telescope showcases a couple of benefits over earlier telescopes. Its size is the main remarkable part. JWST has a 6.5 m mirror composed of 18 gold-plated hexagonal parts. This behemoth can gather light from distant objects various times faster than the 2.4 m central mirror of the Hubble Space Telescope, since it can collect more than 6 times as much light. At any rate, the substantial game-changer is JWST's sensitivity to infrared light. The space telescope can detect frequencies between 0.6 to 28.5 micrometers, spanning the mid-infrared to the red end of the visible spectrum. While a large portion of Hubble's responsiveness beams on visible light, its optics are tailored to capture radiation from 0.3 micrometers in the ultraviolet to 2.5 micrometers in the near-infrared. Astronomers can see galaxies that formed less than a billion years after the Big Bang by utilizing the infrared range. These faraway objects send visible and ultraviolet light. However, due to the expansion of the universe, this radiation is now emitted at longer infrared wavelengths. This makes infrared an excellent method to see these young systems. Close to Earth, infrared observation also applies to newly formed stars. Baby suns are surrounded by dust, which scatters visible light, obscuring our view but allowing infrared energy to pass through. Infrared radiation is invisible to the human eye, and the colors of images received by JWST shift from what the normal eye would see to reimagined views. Scientists often map longer infrared wavelengths to the red end of the visible spectrum and shorter wavelengths toward the blue. This model is adjusted to include specific nuances. JWST serves as a broadly useful observatory, not centering solely around distant grandiose systems and star formation. Its strong infrared capabilities enable it to observe features in nearby planetary systems that conventional telescopes cannot notice. It focuses on cloud belts on gas and ice giant planets, examining cloud patterns on Titan, looking at Pluto's atmosphere, and probing many more small asteroids and trans-Neptunian objects. These are just a few of its initial achievements. When NASA's Double Asteroid Redirection Test collided with the asteroid moon Dimorphos, JWST even caught a brief glimpse of the event. This allowed NASA to focus on the potential of altering the trajectory of potentially hazardous asteroids that could cross Earth's path. Despite the efforts of planetary scientists to uncover the crowd secrets of our sun-centered system, more than 5,000 known exoplanets in our galaxy remain dark. The vast majority of this additional information lies beyond the limits of Earth-based telescopes, including Hubble. At any rate, JWST has already begun to transform what is happening. While not explicitly intended for exoplanet discovery, JWST identified one around the red dwarf star LHS 475, which is 100 light-years from Earth. This planet's size is just 1% smaller than Earth's. However, it orbits its sun in just 2 days and exhibits a temperature a scant 100 degrees hotter than Earth. JWST's greatest strength lies in its ability to study exoplanet conditions by taking note of strong atmospheric signals. Cosmologists can explore the chemical composition of these worlds, as many compounds essential to exoplanet research are found in the infrared spectrum. JWST's unexpected findings have included the detection of various compounds on exoplanets, including water, sulfur dioxide, carbon monoxide, sodium, potassium, and carbon dioxide. The gas and dust clouds known as nebulae are where planets and their host stars form. However, despite their grandeur, these clouds obscure the early processes occurring within them from our view. JWST's infrared vision has begun to reveal these hidden conditions. For example, the Eagle Nebula, famous for its pillars of creation photograph taken by Hubble in 1995, was one of JWST's initial targets. While Hubble primarily saw dusty clouds and gas, JWST found several stars that had proactively emerged from their natal cocoons. Stars observable outside the shadowy marks of HELP are unmistakable by their diffraction spikes in pictures obtained by reflecting telescopes like the JWST. These revelations offer significant insights into the plan and advancement of celestial bodies, uncovering understanding into the mysteries of our universe. In their objective, stars structure into developing stars. However, the JWST has seen much more recently outlined objects called protostars. These protostars are still in the process of accumulating gas and dust from their surroundings. Each so often, they emit material planes that strike their thick environment, making them communicate serious red sparkles. The 2 lower points of HELP are among the best examples of this idiosyncrasy. These protostars are estimated to be a couple 100,000 years old, as shown by cosmologists. Star formation happens throughout the universe, and JWST scientists are eager to explore it. Various signs past our world, inside our local group, include the massive and small molecular clouds, both generally immense satellite astronomical systems of the Milky Way. It is crucial to study these regions since they contain about half of the metals produced by massive stars in the Milky Way. This current situation seems to mirror conditions that existed when the universe was only 2 or 3 billion years old and galaxies were forming stars at an extreme rate. The cosmic systems formed during this significant early epoch, including those we see now, were shaped by the interactions during this period. The Tarantula Cloud, located in the Large Magellanic Cloud, is the closest object in the molecular clouds that reflects these violent times. The Tarantula Cloud is the most significant star formation zone in the known universe, creating stars at an intense rate. About 820,000 stars have been catalogued by astronomers to date, and the giant reservoirs of hydrogen and helium in the cloud should be sufficient for many more. The massive star cluster R136, near the center of the cloud, contains numerous stars, each with masses of at least 100 solar masses. JWST's initial insights have uncovered unique details of the Tarantula Cloud. In the heart of the cloud, a sizable cavity has been cleared out by the extreme radiation and stellar winds from the massive stars in R136. This region is undoubtedly the densest part, which likely contains young stars of its own that can endure this onslaught. The tarantula cloud provides astronomers with a close-up perspective of the conditions they would experience as they further explore the grand cosmic landscape. Insights gained from nearby phenomena often help scientists understand more distant ones even more clearly. Similarly, star formation in the molecular clouds reveals insights into related cycles in the far reaches of the universe. Planets in our local planetary group contribute to the examination of exoplanets, and research on baryonic matter directly adds to how we could interpret the nature of the universe's beginnings. JWST was designed to focus on old systems formed at the dawn of the universe, and scientists have been thrilled with its findings. Out of these tests, the inability to connect areas can often serve as analogs for older, more distant epochs. A significant field image of the galaxy cluster SMACS J0723 in the southern hemisphere was one of JWST's most important pictures, alongside the first made public. This image, which took 125 hours rather than weeks, revealed numerous systems. These far-off galaxies, even fainter and farther away than what Hubble could perceive, are discernible in the SMACS J0723 cluster. The light we receive from this cluster is from around 4.6 billion years ago. However, due to the cluster's massive mass acting as a gravitational lens, systems seen further away, including those formed within a billion years of the Big Bang, are visible. The smallest galaxies in the field appear furthest away and do not seem to be the more mature, curving, and bended systems closer to our planet. A critical discovery made using the galaxy cluster's gravitational lensing is the detection of two galaxies formed just 450 million and 350 million years after the Big Bang, respectively. These galaxies appear remarkably awe-inspiring and likely began to form just 100 million years after the Big Bang. Researchers are uncertain if these galaxies contain many faint stars or just a few exceptionally bright ones. 3 stars, believed to be the first stars in the universe, were made solely of hydrogen and helium. Another new finding by the James Webb Telescope is the imaging of a collection of massive galaxies nearly 600 million years after the universe's inception. While the actual age may not be particularly surprising, the circumstances surrounding this discovery are significant. By pointing telescopes toward the universe's beginnings, we can observe events that occurred billions of years ago as their light reaches us over time. These ancient galaxies, only 600 million years or less from the universe's earliest moments, pose a challenge to our current understanding of galaxy evolution. Their rapid development raises questions about the cycles involved and challenges long-held theoretical models. These discoveries highlight the fundamental mission of the James Webb Telescope, to push the boundaries of our knowledge and challenge established scientific understandings. What more JWST will find remains unknown, but it's certain to continue reshaping how we interpret the universe through its precise insights and significant imaging capabilities. JWST is poised to unveil more secrets of the universe and perhaps transform our understanding of its early ages and cosmic evolution processes.